All right, welcome back, everybody. We're in the last week of classes. Any questions before we get started? So the plan is I'm going to finish about 10-20 slides about hardware security, about defenses and so on, and then we're going to move on to the paper presentations. As I said in Campus Wire as well, these things I'm going to cover today, including the presentation, won't be covered. Won't be included in the in your final quiz, which is Thursday. A couple of reminders: your quiz is going to be in class on Thursday, but still you can do it over the internet at home if you want to on Gradescope. Same as quiz number 1 and quiz number 2. So basically, same format, kind of like similar timing, stuff like that. Will be released probably at 10:15, and the due would be like 11:45, something like that. And if you want, you can come to the class and take it in class. I'm going to be here as well on Thursday. So I mean, we can answer some questions you might have and so on. Okay. That's the first reminder. Second reminder is about your evaluation, course evaluation. I posted something on Campus Wire. Please read it. I really want to have your feedback. So please take some time and read something. Write something, and give us feedbacks on what you liked and what you didn't like, and so on and so forth. Okay. As an incentive, you're gonna get 5% if you have participation, 75% over. I think last time I checked, we're around 25% over the weekend. So hopefully you guys can catch up this week. I think the deadline is Saturday, something like that. So yeah, just be careful. It's not usually it's like the day before the finals week. Right? Any question, anybody? All right. So last time we talked about hardware security, right? We begin with hardware security primitives. We talked about PUFs and true random number generators. We also talked about tamper-resistant hardware. Then we switched on to an important topic these days, and that's supply chain security. And when we are talking about supply chain, we're talking about the hardware manufacturing supply chain. Of course, for everything else, you also have a supply chain, and it's important to secure all the supply chain. So, for example, the supply chain for manufacturing color and so on. When we're talking about supply chain here, we're talking about hardware manufacturing supply chain. And we said that it's very, very important just because, as like in the last slide from last time, we said that basically only 18% of chips are manufactured within the United States. And this was actually quite a challenge because this thing called hardware Trojan, which essentially either the designer or the manufacturer can change the hardware in some malicious way, and unfortunately, it's very, very difficult for a user, for an end user, to find and realize that the hardware has been changed. Okay, we discussed details of how you can change the hardware, and we said that it's actually getting worse and worse just because the technology is getting even more expensive, and only if 10 years ago, more than 20-25% of the chips have been manufactured in-house locally, these days just because you're shifting to 5 nanometers and 3 nanometers and so on, the cost unfortunately is significantly high. So it's just only economical to have maybe just one large manufacturing company building everything. Okay, and that's what's really happening. So these days only TSMC and Samsung, in some sense, is doing this very high-end manufacture. So to give you a real example, so this is a story, what's called a big hack. It's actually an article published by Bloomberg, I think in 2016. It's a story about how a manufacturing company actually added some hardware Trojan in motherboards. And it's actually impacted servers, especially for Amazon. And an official report says that it's actually millions and billions of dollars has been impacted. The company, lots of information actually been stolen and so on. The interesting about Big Hack is actually it's never been confirmed. So it's actually, U.S. intelligence, your Department of State, White House all of them kind of like debunked this story. But Bloomberg had multiple articles actually about this, and they even recently they kind of doubled down on that the story is indeed true, and they didn't say it's true. So I mean, assuming that it's true, so we are not endorsing that whether this story is true or not, but assume that potentially there could be an attack like this. Even if it's not true, in practice it could happen. So what happened was that basically this company called Company X, they were like in a very big manufacturer of video motherboards, especially for servers, rack style computers. What I mean, this big hack attack happened was what was this big hack attack was is that there's this additional chip, which was kind of like an RF chip. So we were actually listening to the communications on the motherboard, and it was actually an RF signal. So we're actually sending it out to some unknown place, so some specific IP. The size of the chip, the added chip was like this size, and then you can see actually the tip of a pencil to just give you some perspective of how small this was. And also compared to the large motherboards, it actually was like added somewhere here inside the motherboard. Okay. And then basically what happens is that according to the reports that majority of the motherboards being bought by Amazon during 2016 and 2017 was actually impacted by this attack. Again, story may or may not be true. So I mean, just imagine that this company is actually Company X and this company is Company Y, and this happens. I mean, in theory, basically, not in practice. So what will happen is that the manufacturing company actually add all of these tiny chips to their motherboards, and all these motherboards goes into this large servers. And if you remember, we talked about machine learning as a service and generally computing as a service as something that these days are significantly becoming more and more popular. For companies who provide these services, that's exactly what these attackers want. So, for example, this company is also providing platform as a service where you pay and you get some computation platform to do your stuff. What will happen is that basically this means that the attacker not only has access to the information within that server or that cloud system, but also has access to all the information to all the people who are using that cloud platform. Okay, so the potential impact of such an attack is very significant, is very important. Okay. And realizing and finding these tiny changes is not a trivial task. Which is very, very difficult, because obviously you can see that it's kind of like finding a needle in a haystack kind of situation, which we were talking about very, very tiny piece of electronics in this very, very complex circuit system.
Did they figure out that there was like a malicious
So I mean, again, it's kind of like more of a leakage kind of thing. So somebody told that all the potentially leads. So apparently the company who was like the victim of this attacks, they internally figured it out, and they contacted intelligence agency and so on and so forth. I mean, the Bloomberg article is actually available online. If you're interested, go and Google it and read it. It's a very interesting story. As I'm saying, as I said before, this is not a confirmed story, so it might be completely untrue. But again, for this class, the idea is, yes, it could happen even in future, right? It's not something that we're generally talking about the potential. All right, so future trend, as I said, it's getting unfortunately worse. So stories like big hack can actually happen in future more and more often. The three reasons that I kind of like also discussed already is we are getting more and more complex systems. So these, for example, this motherboard is getting more and more complicated, more denser. We are moving toward expensive nodes, 3 nanometers, 1 nanometer, so on and so forth in the future, and all of them require very, very high-end manufacturing facilities. And we also are going to use new technologies like machine learning as a service, platform as a service. All these things will actually also help the attacker to change something in hardware and actually use it in the future. Okay, so future of hardware security is becoming more and more important these days. And that's why like one of the keys, one of the most important, issues in securing systems and computers, and especially at the US government, is about hardware security. Okay, so now we kind of know what is Trojan, why it's important, and so on. Let's actually finish the lecture with how to detect and how to protect against Trojans. So there are multiple different ways. The first one is what's called a physical inspection. It's literally, searching through the hardware, either the board or the actual chip, and trying to see if there is something that is different than what you're expecting. Okay. So this could be usually very invasive, solution. We are taking out metal layers, we are taking out wiring, we are taking out the packaging in order to take pictures, move forward, and find actually the changes. It's like same as like trying to X-ray, for example, body, or trying to X-ray something and try to find specific tumors, specific items in malicious items in your system, right? So this is exactly the same idea. You have to remove and destroy the hardware in order to find it. The idea is that the reason that destroying is not an issue is that, for example, if you order a motherboard or if you order a chip, you're going to get thousands or more than thousands of these. Okay, so you're not going to get just one chip, right? You're going to get lots of chips, and potentially if one of them is malicious, all of them will be malicious, right? So, I mean, the attacker doesn't want to just make one of them malicious, probably just wants to make all of them malicious. So that's why you're kind of sacrificing one to save the other 999 system, right? So you kind of like to do invasive, inspection and try to find the potential malicious hardware or malicious changes. So this could be, for example, happen to detect these kind of Trojans that I showed you here, right? So, I mean, if you remove layers by layers, you actually goes into here and see, there is this additional 2 gates that's wasn't supposed to be there, right? So it kind of like this physical inspection kind of eventually reveal this for you. So it's kind of like, you reverse engineer your system to try to find what you have built, see all the gates, all the connections, and this way you can say, okay, there's something that's been modified in your system. Okay, same story can happen for your motherboard. You basically need to remove every single chip from this device and see whether that chip was part of the original design of it. Okay, it's kind of like basic physical inspection. It's nothing fancy, but of course you need high-end X-ray systems, high-end imaging systems in order to be able to have a before and after kind of design process and comparison. Okay, so this is actually becoming very very popular these days, just because it's actually very effective and it's guaranteed that you can find a potential solution. Okay, any questions? Okay. The second thing is, yeah.
What is a net list?
Netlist is when you're building your hardware, you start with the hardware description language. Then there's some sort of like a compiler version that you compile this from the hard level language to what's called a netlist, which is basically just a list of gates and connection between them. So at the end of the day, what you're gonna build in a hardware is list of gates. It's basically equivalent of instructions when you're writing a software and when you're running it on the processor. At the end of the day, you're just running things at the instruction level. When you're building hardware, it's also kind of like you're building things at the gate level, and you already know how like your AND gates should look like, how your NOR gates should look like, and so on. Does that make sense?
Yeah. Thank you.
Okay. So the second thing that you can do is that instead of like having some sort of an invasive process, what you can do is what's called a functional verification. So basically, what you want to do is having some sort of a model and having so this is basically the manufactured one, and this is your reference model. How you get your reference model is a separate story, but let's say you actually have access to something that is not malicious. what you want to do is basically seeing that whether this is functionally equivalent to this one. Okay, how would you do that? So you can use different, kind of like source of information. One of them is actually, interestingly, side channels. So what you would do is that you have a reference model, usually called it golden model. So this golden model is this exact same hardware that you build in some sort of a somewhere that is trusted. And what you would do is that then you build, a large number of, same replica of the same chip, and these two are supposed to be exactly the same, but you're not sure whether these are actually the same as this one or not. So what you would do is that you need to kind of compare these two, kind of apple to apple comparison to see whether these are exactly the same or not.
If you're relying on hardware that's coming from an outside manufacturer, how do you manufacture your own chip?
That's a great question. So having a golden model is an issue, but I mean, there are various ways of doing that. At least one thing you could do is you may not know which one is malicious and which one is not, but you can at least compare them together. So you can classify these chips from each other. So for example, you can say that, okay, out of these chips, at least this one and this one are similar or not similar. And one way of actually achieving golden model is the previous model, basically. So what you would do is you, for one batch, you do invasive, and then you go through the whole process and making sure that whether this is malicious or not. If it is not malicious, then you have trust on that batch. Then the next batch comes in, and then instead of doing an invasive process this time, you're going to do a functional verification. So functional verification is much less costly, less time consuming, and so on. So basically, kind of like, iteratively, it's better to do it that way. So the first time you do it invasive, the second time you do functional.
Do invasive verification. You're saying you like basically you also like you take down the chip like up to its gate level design. Like,
Yeah.
with silicon, right?
Yes.
So in that case, how do you put it back together?
You don't put it back. That's why it's invasive. You destroy it. But the idea is, as I said, you don't get one, right? So you get a batch of chips.
Okay.
You get like thousands or millions of these chips.
Uh-huh.
You randomly select some of them, and then you do this invasive process for them. The idea is that if your random sample is large enough, then it's kind of like very likely that you will find that potentially malicious. Of course, if the adversary only create a malicious hardware just 1 out of million, then your chances of detecting is so low. But the idea is that for the attacker to also kind of economically make sense for the attacker is that the attacker wants to have the majority of these chips malicious, right? The attacker. Yeah, or even the designer. So even if the designer is the malicious, player here, then all of the chips should have been, malicious. So if one of them is not, then it's guaranteed that the others are in this. Does that make sense? So basically the idea is this. So you have, a list of chips, right? N of these, right? A malicious user have two different options. Either you're gonna just make all of them malicious. So in that case, if you randomly sample one of them, let's say this one, and then do the invasive process and say, okay, this is malicious, then you know that all of them cannot be trusted. If this one says it's okay, then more than likely the others are also okay. The other option is that the attacker can be a little bit more stealthy. Say that, okay, I'm not gonna infect all of them. Maybe I infect every other. But again, if you have random selection and this random selection is large enough, the chances that you find at least one of these malicious is pretty high. It's kind of like, again, it's a game that you need to play. You're not 100% sure that every single chip that you're gonna use is malicious or not, but at least you can have a decent amount of confidence that this is not malicious.
So do you usually do this to prepare for the functional verification?
Could be that this could be also feeding into the functional verification. So for example, you say, oh, okay, this one is not malicious, so maybe I can compare everything to this one.
Right. So basically, it's like that the invasive process destroys your chip.
Yes.
You can't use it anymore.
You cannot
It's
use
like
it.
you're doing that to 1 up to 10,000 chips.
Yeah, exactly.
Take the loss and say, use this for reference model for all the.
Sometimes if you destroy it, you cannot even use it for your reference model. That's also another thing. But at least you can use your functional verification to kind of categorize it. Okay, these groups are all similar to each other. This group is also similar to each other, but they may not be the same. So what you would do is that a representative of this and a representative of this, I'm going to do the invasive model, right? So yeah, so interestingly, as I said, side channels could be one way of detecting Trojan. So for example, we talked about like electromagnetic side channels, we talked about power side channels, right? And we said that essentially these are application and hardware specific, right? So what you can do is just saying that, okay, because of the same reason that these are hardware specific, how about we actually use this as a reference? So we're going to run multiple different things on multiple different hardware. They should create exactly similar side channels. If they don't, then that means that one of them is potentially different and potentially malicious. Okay, so that's kind of like the idea of using side channels. Of course, there are lots of challenges, including how do you have a good coverage? Because if you remember, we said that essentially Trojans are mostly, mostly inactive, right? So they're not actually, active all the time. So the chances that if you run them and you don't get any difference is pretty high because they're dormant. So what you need to do is actually running it for various different, inputs, such that there is a condition for the hardware to be triggered, right? So it has its own challenges, especially in terms of generating inputs, but there are methods that people actually show that it's possible to detect these hardware Trojans. Okay. So going back here. So that's the second option. The third option is what's called split manufacturing. Okay, so the idea of the split manufacturing is that the way that we're going to design hardware these days is we're basically saying that, I'm going to have on my hardware design, then I'm going to get my net list, which is basically a list of gates. Then there is the place and route and things like that. Then at the end of the day, you get this file called GDS2, which is kind of like, combination of like all your gates and how they connected to each other, which metal layers they're using, and so on and so forth. You send this to the manufacturing company, the foundry, and the foundry is going to take this and then give you back your chip. Okay. What you can do is the idea of the split manufacturing is that when you're sending the entire design to one foundry, the foundry can basically do whatever they want with it. So the idea is that, I'm not going to send the entire design to just one foundry. So I'm going to divide this into two pieces, send one piece to foundry number one, and then the second piece to foundry number two. And they're going to send me back the chips, and I'm going to just manually, combine them together. Okay. Another idea is that usually, chips are these 3D designs, right? So you have the transistors at the bottom layer, then you have metal layer 1, metal layer 2, metal layer 3, and so on and so forth. Okay. So what usually the idea is that you send it the design for the transistor level and maybe the first layer of metal. You don't give any information of how these metals are connected to each other on layer 2 and above for foundry number 1. You get the design from foundry number 1, which has only the transistors and metal connection of layer 1. Then you send this design to manufacturing company number 2, and the information about the connection in higher level metals. And then the foundry number 2 gonna just combine these things together for you. And then you have the full chip that as you would normally get if you send everything to your foundry at the first place. And this way, there are actually, security guarantees that this problem is reduced to some sort of a graph problem. And people have shown that, under some circumstances, the attacker cannot really figure out what is the actual connection between gates and so on. So in other words, it would be very, very hard for the attacker to change anything meaningful in the design because the attacker has never had the full control over how to build this hardware.
But this is based on the assumption that you're able to, for example, multiple founders.
Yeah.
Or is there only like a couple foundry companies that are viable?
It is, but so the trick is it's nice. So what would happen is this bottom layer, the first part is actually it's the only part that has the transistors in it. The rest of it is just metals. So the first part is actually sent to high-end manufacturing company. The second part is actually can be technically, built anywhere else because, connecting metals to each other doesn't require that much time. So you can do it you can all do it, most of it actually, like in a university facility as well. It's not that significant. Okay, so the idea is that, the untrusted part, the important part would be this part that I'm going to send it to like a high-end manufacturing company, and the second part is I'm going to do it myself. Does that make sense? Okay, so this is the idea of split manufacturing. You basically split your design and you build it in two different, you basically break up the design, break up the truss, right? So remember, going way back at the beginning of the this class, we talked about multiple truss, distributing the truss. So basically, this is one example of that. Any question here? Okay, so there are multiple challenges for all of these. Older model, we already discussed that. That's one of the big challenges. Dormant Trojans and the coverage is another big challenge. So, I mean, detecting Trojans is not a straightforward task because Trojans are designed to be inactive for the majority of the time. And that's why you may not be able to detect Trojan all the time. And then the third one is kind of like this, what's called an unknown problem. So you don't know what you're looking for, basically. That's the biggest problem. So, and for example, in the big hack scenario, right? So you don't know what you're exactly looking for. So it's not like you know exactly, oh, I'm looking for this specific chip. You don't know whether that specific chip exists or not. That's the first problem. The second problem, you don't know if it existed, what would be the signatures and how it would look like, right? So we kind of like, have this unknown problem versus, a known unknown problem, which you know what you're looking for, you just have to find it. The unknown problem is basically telling you that not only you don't know what you're looking for, but you also don't know how it looks like. So it's a very, very challenging problem, but it's something that you have to come up with innovative solutions for fixing this issue. Does that make sense? Okay. So the last thing to talk about is other than hardware Trojan, another problem with the supply chain security is generally reverse engineering and what's called IP piracy. So for example, company number one designed this very high-end chip and send it to the foundry. What foundry can do is that they don't necessarily need to insert Trojans, but what they can do is that reverse engineer this, find the actual netlist, and maybe sell this netlist to their competitor, company number two. And company number two can use this in order to build a better chip compared to company number one. Okay, so basically it's like a similar way of stealing the IP at the software level. We talked about how software could be important and could be an IP. You can also steal the IP of the hardware, like the actual design of the hardware. And of course, for open source design, it's not an issue, but like think about like these large, hardware companies that they're competing to each other. And then if one can actually get full information of how the other design works, then they probably can use that information to build a better system, right? To beat their competition. So that's another major issue with this system.
Is the only solution to this just to like manufacture everything in-house?
No, yes and no. There's a whole bunch of what's called obfuscation. Do I have it? Yeah. So the common defense mechanism is actually this slide, which is what's called hardware obfuscation. So you basically don't kind of like at very high level, it's kind of like encrypting your design. So basically, only you have certain information about your system, you can know exactly how the gates are designed to each other. There's this thing called logic locking. Because of the time, I'm not going to go through it. But generally, the idea is that you don't exactly know what this gate is unless you have some information about some sort of a hardware key that shows you that what this is. So basically, so it's kind of like this gate is connected to another gate. And usually the key is here. So in order to know what exactly the output of this gate is, you never actually have access to here. You only have access to here. If you have a key, then you can exactly know what this output is, and then as a result, you can know what this gate is. But if you don't have the key, then essentially this is just a random process. You have no idea what this gate is, right? But remember, what you want to do eventually is being able to detect all the gates in your design, right? So if you cannot find this gate, then you probably cannot detect other gates. And so on.
I have a question about the previous topic where we were talking about how to like check if the foundry or something like added.
Mhm.
Are these like the solutions that we talk about, like checking one against one, like sacrificing one for the others? Is it like common practice in the industry?
Yeah.
Like, do they always do this stuff?
Yeah.
Okay, so usually all of them, they don't trust the foundry.
Well, I mean, I'm not aware of the internals of like these big companies. I'm guessing that for like, consumer grade, like laptops and so on, they probably don't care. For military level applications, they probably care and they do all this. So for example, if your chip's gonna go to this fighter jet or this tank, then they're probably gonna like do all these things.
Yeah.
If they're gonna just put it on a laptop, then probably they don't. All right, so the first defense, as I said, is hardware obfuscation, which essentially the idea is, I mean, it's make it very, very hard for the reverse engineering. The second idea is kind of like a verification and detection, both at the pre-level and post-level. So in test generation is a big thing, symbolic execution as we discussed. So basically many of the things that we do at the software level to make sure that our software is not malicious, is not compromised, we can kind of do similar approaches. Of course, the implementation and details are slightly different, but the ideas are kind of like the same, that we do some sort of like a software level analysis, including fuzzing and symbolic execution and so on, in order to see that there's any issue with our design. Okay. So that's kind of it for hardware security. The main message is, supply chain security is becoming more and more important. It's been important in the past, but it's becoming even more important these days. It's a very interesting area of research. So if you're interested to learn more, I definitely recommend you read about, for example, Big Hack and all this other newer stuff. Yeah.
If the IP, like the design of the something was stolen and competitor company sees it, like presents a new lecture, says you have a great success in R&D and got like 100% increase in the performance.
Yeah.
Can the original company see one somehow like reverse engineer their chip and argue that they probably stole our design?
So there's always, they can
Like, how
probably.
can they tell us it was stolen or not?
That's a legal argument. Unfortunately, I'm not an expert in that domain, but you basically can, there are ways that you can say, designing, testing a specific product, I don't think it's illegal. So what you can do is that saying that, with this, specific test this fancy test that we have created, we show that this is actually very similar. But it's generally very hard to show that these designs stolen from us. I don't think personally that this would be an easy case to prove that these are the same thing, because many of these designs are actually, very standard these days. So you kind of like, you add more cache, less cache, things like that. So, and then you cannot claim that, we improved this cache. Unless it's a specific patent and then they use your patent and you can prove that. Otherwise, it's not that easy. But again, these are probably, if we talk to high-level management of these large manufacturing companies, they probably have better insight. Maybe for future, we'll try to see if we can have some nice talk about that. All right, are we good? So it's kind of like it for hardware security. Any final question? Awesome. So let's let's move to the paper presentation. Who's first? You guys? Okay. Do you have it on my,
I
on
should,
my,
I
okay,
should,
so let me stop sharing. Just a reminder for everybody that if you haven't already uploaded your slides, please do it. I don't have it as, should be 9.1. Oh, you shared the Google Slides with me?
we should both sides.
Okay.
You want us to upload it thing?
Upload the PDF on that shell folder, but I can just open it. That's fine. Okay, cool. There you go.
Alright, hello everybody, we read the paper on modulating analog RF hardware trojans in wireless networks. So basically it's a paper about what we just learned in class, but for wireless network security. And we're going to talk about a solution to that. So
Yeah, so the paper talks about the problem where the attacker can basically tamper with your RF systems and establish a covert channel to like leak data from your device to some other to the attacker's device. So the system they introduced in the paper is the system right here. We have a baseband processor, which I'll go a little more into details with, that communicates with the analog RF. And in the paper, I'll go more into this, but the paper, they introduced two Trojans, one attacking the baseband and one attacking the front. So the baseband processor is responsible for implementing the wireless protocol, so most of the digital stuff. It runs a real-time OS on the device in order to control the different devices on the analog RF front end is analog. It has the filters, the amplifiers, and it's more hardware. So this is a basic overview of the communication system. You have some source. You do some encoding, such as error correcting bits, as well as just choosing what bits represent what. You modulate it so that it can get transmitted to a channel, and then you can decode it. And then get rid of the error correcting and channel codings, and then get the what the sender sends. This is just a brief overview of modulation, since the paper kind of went into it a little bit. So in this case, is the paper talks about the quadrature amplitude modulation, which is essentially like at the basic level, you get some bits. So let's say you want to send like 0, 0, 0, 0. This one right here. That bit is associated with a specific phase and amplitude. And then if you're trying to send that bit, it sends that phase and amplitude over the channel. And then you can decode that. Paper kind of talked a little bit about the quadrature sign or quadrature and in-phase component, which is just the sinusoidal component and the cosine component. It also talked about amplitude shift keying, which is similar, except that when you're trying to send a signal, so if you're sending 1, you might have a bigger amplitude than if you send a 0. And then it talks about impedance matching a little bit as well, which is, so if you have an output amplifier as well as a fixed load on the output, you want to match the impedance such that the most amount of power can be transferred between the output and the amplifier. On a side note, if you don't match it, less power is transmitted, which is how the Trojans will work. Next few slides. So to bring all these concepts together, the first Trojan to introduce was on the RF front end, so the circuitry side. So if you look at the R Trojan, you have a power amplifier as well as a resistance that you're trying to match. And with impedance matching, you don't match the resistance, so you have one resistance lower than the other, and you pass through the power amplifier, you will transmit less power, which is how they leak the data. Trojan 2 does the same thing. It modulates the power based on the leak data. In this case, the Trojan resides on the baseband processor, which communicates with the RF front end. And if the Trojan is on a baseband processor, they can send control data through the SPI interface and change the gain on VGA, which is the variable gain amplifier, which will modulate the power. So both Trojans modulate the power. And yeah, so both Trojans modulate the power basically, but they reside in different locations. The paper then goes into a theoretical analysis on whether or not the Trojan will work in practice or theoretically. For a legitimate receiver, it uses the quadratic amplitude modulation, which is on the previous two slides, as well as QPSK and PPSK, which is just variations on QAM. And this again, it's just the receiver will decode the frequency in the phase. They found that the differences between a Trojan-infested device and just a normal device is pretty negligible. Like they can just argue it as noise, which makes a Trojan a little more powerful since it's harder to detect. On the receiver side, because we're modulating the power, it uses ASK, which was introduced in the previous slide. So it bases the amplitude of the signal to the leak data. And again, they also did a theoretical analysis on that to make sure that using ASK with the power modulation, it's enough to have a low enough bit error on the receiver, on the road receiver.
So in this paper, essentially what they did, as Wendy said, was they created two Trojans. They in-house they developed the Trojans and then they went on to evaluate. And that's that, I mean, in my opinion, that kind of adds to the really paper because they formed these very robust attacks. And then they thoroughly evaluated it, which I'll go into detail in a bit. But so then they came up with a solution kind of for their in-house attack, which is a common attack something that's been done. So what they propose is ACE, adaptive channel estimation. This is a bunch of words, but essentially what it does is it exposes the presence of hardware channel fading and noise. Wi-Fi is effectively slow; it goes around for a while, and so ACE is channel estimation algorithm. It's kind of slower than packet rate, and it kind of analyzes the signal that's received based on this equation here. It says the signal received is equal to H, which is a channel matrix. It's essentially just some multiplicative factor that changes the signal in some way, multiplied by the original signal plus some term for noise, and is Gaussian noise. So if you switch to the next slide, when you receive the Trojan on the other end, there's some Trojan, there's some multiplied term added in there, and it's H times T times X, and that T accounts for Trojan activity, but it's hard to tell. I mean, if you're on the receiving end, H times T is just equal to it's just one multiple factor. So the question is, how can we identify that there is Trojan activity? And so that's kind of the whole mathematical purpose of the paper. Yeah. So the way that the algorithm works is first we want to remove the Gaussian noise and using adaptive averaging. So we basically compute noise variance and estimates, and then over time we learn to them. Second is then we can then determine the channel matrix, and thirdly we can remove the channel matrix from the noise estimates to reveal the Trojan activity. And as for how that's done, well, it's sort of somewhere. I mean, actually, to functional verification in class today, it's essentially compared to a Golden model. So yeah. And so then the actual analysis is then done kind of based on the graph. For each estimate, ACE produces, for each packet, ACE produces 64 carrier locations, and they plot them on a heat map. And so in this heat map here, it's highly varied. That indicates Trojan activity. If there was no Trojan activity, it would basically be a solid color. This is a little bit too technical. At high level, what happens is a Trojan essentially it changes signal that makes that periodically. It changes the power in some way that leaks information. That periodic change causes that variation ultimately in signal because there's noise and there's noise and there's noise and so on and so on, and that's how the Trojan works. And so if it's just a solid color, we know that the signal is not being periodically pinged in a malicious way. So as for actual testing, ACE was tested on 2 Trojans that were again developed in-house, which is pretty cool because they went and they developed these robust attacks and then they evaluated them thoroughly. And it turns out that the attacks they used were actually quite well rounded, very few holes, and they also went to test kind of the most severe attacks out there. So it was tested on 2 Trojans, like Michael said, RF front-end circuitry and variable gain amplifier Trojans both kind of modulate power and leak information that way. And then what they did was they evaluated these Trojan cases against a control case with sort of like perfect hardware. So maybe this is a subset of functional verification. We just don't know today, but I thought that was a pretty cool connection there. But yeah, the evaluation was done this way, and in the end, ACE was evaluated to be successful. It was a good detection system. It's not mentioned by any means, but it does detect that Trojans are very successful. As for potential future work, the most obvious one is evaluation on other types of Trojans because they tested on 2 very specific Trojans. Albeit these were severe attacks or it's kind of big that we have protection against these attacks now or detection for these attacks, but I think it's worth asking. Secondly, and this is something that the paper itself kind of discusses, that this focuses on detection during simulation, not during fabrication. So there's not really much out there, at least in this paper, to analyze the hardware itself. I mean, even professor himself was saying, you can't just look at a piece of hardware and go, oh yeah, this has a malicious chip on it. So that's another kind of point of discussion. Thirdly, systems for elimination, once the detection is confirmed, just kind of like a natural next step. Once we have knowledge of the hardware Trojan is there, how do we converse, and what can ACE tell us about what the hardware Trojan might actually be, and how can that information help us? Yeah, I mean, we want to open it up to discussion. This is a pretty cool concept, so I mean, yeah, just how might my discussion question was how might the performance of ACE shift for simpler Trojans and simple hardware, because it was again tested on pretty complex systems. So
All right, thank you so much. Any question, guys? Just one of the examples of how in real world you can design Trojans, right? I gave you some examples in the class that oh yeah, potentially you can add this, but these guys actually show that you can indeed use it. And the interesting thing about the paper was not only you can change the digital part of your hardware in order to create a Trojan, you can even change the way that, for example, you're modulating signal and using an RF signal, and you can change that. You can maybe change the way audio encoder works. Maybe you can change how the camera works and all those things, right? So technically anything that you can manufacture and you can change during the manufacturing, there's the potential of changing that during that phase, either at the design phase or at the manufacturing phase. And you can do something useful, right? Useful in terms of attack. Okay. Any questions? Okay. So who's second? You guys are?
Yeah.
Oh, you guys are? Okay, let's have a quick break of like maybe 5 minutes and then go back with you. Did you uploaded on? Okay. Okay. Yeah, just do this way. Okay. All right, guys, let's start with the second presentation.
So hi everyone, and the paper we're going to present is model attacks on physical and global computers, which is known as house. So then, is it
I
down?
think you have to not select cursor to no, just left the.
Oh, okay. So then some background and some conclusion of the paper. So then The background is that there are different types of puff, and then in particular, we're going to cover strong puffs, and then there are some characteristics associated with strong puffs, which is complex challenge response, and also there's many pairs of challenge response pairs, which is known as CRPs. So then, the main overview is that there are different models to actually attack puffs, and then for arbiter, XOR arbiter, and diagonal arbiter puffs, linear regression actually outperforms the support vector routines and also evolution strategies. And then for V4 arbiter puffs, only evolution strategy works, whereas linear regression and support vector routine cannot even model it since it's not linear separable. And then for ring oscillator puffs, we can just brute force it since there's not a lot of CRPs that we can do it. And then what the contribution of the paper is that they are able to successfully do model attacks on all the known candidates that we presented in the paper. So in the paper, they actually didn't talk about how they do the machine learning, but then they do a lot of testing and evaluations on how effective their models are against this puff that we're going to introduce in the following slides. So then the flow will be we introduce each puff and then the characteristic of it, and then we'll talk about the results from the ML attacks. Namely, we're going to talk about the time to training, how many CRPs are going to use it, and also in response to the errors that we injected in the data to mimic the physical environment of how models react to physical CRPs. And then also we're going to talk about the scalability of the model. So how CRP we increase can actually decrease the prediction error.
All right, so let's start with the first cup. So first one is arbiter cup. Basically, this one is what we actually talk about in lecture. So in summary, we just have two paths of multi-stage muscles. They have a different delay for each stage, so that when you have to output to the last stage, last will determine whether 0 or 1 depends on whichever signal comes first. The key takeaway of this is that you get for the same structure, you have different output for each path. So how can you attack this for machine learning? It's actually very easy to break with linear regression. So as you can see on the table, in order to reach 90%, it doesn't take much effort. It's like very instantly. But the key takeaway is that as you approach 100%, it's going to take much more CRP, require much more CRP to get the result. And as you can see, the bit length, when you double the bit length, is not with CRP going to be double. And the maximum trading time that you can get is 2 seconds. So switching very fast. And for scalability, for prediction error, as the CRP ratio, CRP is over this number of stage plus 1 equals 0. As this is increasing, the prediction error is going to be decreasing steadily. And for the number of CRPs, with iteration, as we increase the CRP, number of iteration also increase. That was too easy. So how can we make it better? I mean, how can you make the prospect harder to break? So introducing the XOR arbiter puffs. So the idea is that XOR is very common in security. So we added it to basically adding more complexity to the puff. So the idea here is that we run multiple arbiter puffs at the same time, and the output is going to go to the XOR gate. So the number challenge also we set the same set of challenge to each arbiter, and the output XOR is going to be 1 single bit. So the result, linear regression still beat this model. As you can see on the first table, as we increase the number of XOR, which we add more complexity, it takes much more time to complete, and also the number of CRP needed to break is very high compared to other puffs. And so the maximum time that we can train is around 31 hours, which is like 1 a day. About the error inflicted, as you can see, that as we increase the error inflicted, gonna be for 10% for 24,000 CRPs. We don't have any meaningful result. So as you can see that as we increase the area inflicted, the performance is going to reduce, and we need some certain amount of CRP to make the performance better. And if we get it to 2,000, 100,000, it's going to be very so for scalability, as you can see that this one's relatively the same for our hubs, and for this, the success rate is really only meaningful in that area. So this is still breakable, and it's still relatively easy because we make it like 1 day break. So can we make it more secure, and can we break this more secure one? Yes, there is, yeah, lightweight secure hubs. So the idea is the same as XOR arbiter, but the difference is that we set different challenge to each arbiter. And the output for XOR is not a single bit. No, we know it's multiplied. So the result. As we assume that the prediction rate couldn't get higher, it actually can reach 99%. The key takeaway for this one is as we increase the number of XOR, it's actually take much more CRP to make the signal get length. And also when we have 128 bit length and we have like 5 XOR, it's going to take like 2 literally years, which is very long.
Yeah, so something to add on this is that the mathematical way of solving lightweight and XOR arbiter pulse is technically the same, but then lightweight secure pulse are quantitatively harder to actually break. So that in this case, you see that the previous one is 31 hours to actually break it, but then in this case, you need to take about 267 days to actually break it, even though mathematically they're the same easiness, to put it that way. So now I'm going to talk about feed-forward arbitrary pulse. And then unlike the other pulse that the very just send a challenge to it, this one actually depends on the previous delay bits to actually feed forward to the future bits to actually produce a response bit. So then the parameters will be number of loops, meaning how many loops there is for the challenge bit to actually feed forward to the future bits. And also what is the starting and end point of the FF loops. So then for the sake of to control the pulse, we'll just assume that the FF loops will have a set distance between each of the months. So then what is the result of the machine learning model? So then the paper actually tried to perform machine learning modeling through support vector machines and linear regression to it. However, the data is non-linear separable, therefore they can actually break it. However, they can actually do it with evolution strategies. So it's pretty promising to see that there's CRP are pretty consistent, and then training down can actually break the feed forward arbiter pulse. So then something that can note about is that when we introduce errors in our data set to mimic the physical environment, from 0 to 10% is actually pretty similar consistency throughout the prediction rates. So from 89% to 87%, there's technically no difference. So then, however, compared to the previous ones, such as linear regression or support vector machines, the difference is that evolution actually require more CRPs to actually do a training, and then it almost demonstrates like a super linear relationship between how many CRPs actually do, and also what the computational time is actually significantly higher compared to all the other models. So then here you can see that it's actually x to the power that it needs for the CRP to actually reduce the prediction power. So then it's almost like a hyperbolic relationship between how many CRPs I actually need to reduce the prediction error. And now we're going to talk about ring oscillators, even though they introduce it as a strong pulse, but in my opinion, it feels like it's more like a control pulse or a weak pulse in a sense, because there's actually not a lot of control response, challenge response there, sorry, to actually do the query of the pulse. So that this, how it works is that it's based on the influence of the fabrication variation in the inverters. So all the small triangles you see there, essentially inverters and creates like a oscillation within the system. So then how do we actually do a comparator? Is that we count how many oscillations we have in Mux 1 and Mux 2, and just see that, oh, let's say Mux 1 has more oscillations than Mux 2, then we'll output 1. And then otherwise we'll output 0 if it's less than or equal. So then how do we actually break it? We just do a quick sort to sort all the frequencies and then actually achieve like 99.9% accuracy as shown here. But that would be something too simple for them to actually research on it. So that how can you actually do better on it? They apply machine learning model to it, and then which even though they didn't achieve like a similar 100% accuracy, they achieved 99% accuracy here, and then you can see that they actually reduce the number required CRPs to half of it compared to the one that is 246.
So we have summarized all the performance of our machine learning model against the top machine learning paper. And as you can see that algorithm hubs is very vulnerable. Even though the best model ever, you can still break it in 2 seconds. XOR is adding more complexity to it, but it still takes like 17 hours. And the best one is a lightweight model compared to the other two. That is gonna take like months to actually break it. And this is another which 99% completion rate. And also for feed forward auger, we use this different machine learning model. So for the previous three, you actually use linear regression on feed forwards at different times. So we use a solution strategy to take like 1.5 months. So the conclusion that all strong hubs in this paper are very easy to be broken by machine learning with a sizable success rate. In fact, that the author of this paper actually mentioned that this all strong hubs are insecure, but that's his biased opinion. And also that paper is very weak. I mean, that's very old. So we actually have a strong hub going on. This paper is actually the fundamental for evaluating the strong hub. So for XOR based or resilient or machine learning, and increase the stages can lead to increase in training time for the model. And the second key takeaway is that machine learning is also robust against noises.
Yeah, so I'll talk about some of the discussions that I want to talk about. So then, what are some ways that you can actually think of to actually increase the security of the pubs? Maybe it's increasing the stages to make the bits more longer, to make the challenges longer, or maybe it's adding more complexity, maybe adding more gates such as XOR and then to actually increase the complexity of the system. And the follow-up will be what are the drawbacks that come with increasing the security of the pubs? Maybe it's increasing the security will add instability to a system, introducing more errors or maybe introducing more randomness to the system. What are some of them? And then another question is what are some other pubs that we can explore? Maybe it's resilient against machine learning. Maybe it's some not about silicon pubs. Maybe it's some sensor pubs or maybe some voltage pubs that we can actually do to actually be resilient against machine learning. That will be the end of the presentation. Thank you.
Anybody have any questions? Thank you guys. So good job. To just give you a little bit of background, I mean, we have a bunch of different PUF designs. Ring oscillator and arbitrator pop are key examples. And then, so these things kind of like introduced around 2005 to 2010. Then this paper came out and basically showed that essentially using some sort of a simple machine learning algorithm, including like logistic regression and then some evolutionary algorithms and some basic machine learning, like neural network based attacks, you can easily model this puffs, because essentially a research puff is like a very linear function. So all of these are basically some linear functions of some multiplication and some addition. And logistic regression is essentially designed to do that for us, okay, to model that. Then they're kind of like saying, okay, how about we add some non-linearity to the system? And that's where XOR paths kind of like introduced. Basically, what that last stage of XOR does is adding some sort of non-linearity to your arbiter path. So you have a bunch of lanes of arbiter path, like 1, 2, 3, or whatever, and then you XOR them all together. And what this XOR gives you is some sort of non-linearity. And people have shown that this is basically then logistic regression no longer kind of works really well on this because logistic regression is not good for modeling nonlinear functions. So what you can do alternatively is either go with evolutionary algorithms or go with machine learning algorithms because machine learning can also kind of like model nonlinear functions much better than logistic regression. And unfortunately, the results of this paper was adding just simple XOR wouldn't help because then machine learning can easily learn it. So since then, it's kind of like, again, similar to many other aspects of hardware security and generally security that we discussed. It's kind of like, oh, let's come up with a newer model. So there's composite paths, there's what's called an interposed paths, there's what's called an icing path, and all these things. And all of them are kind of like trying to say that, okay, if I use a sophisticated machine learning model, they cannot really reverse engineer and model my code. And they typically come up with a new model, and then there's another person that's kind of like coming up with a clever attack that's kind of like, the reverse engineer kind of models. The state of the art is what's called an icing path, which with SISIYNNG. And the model is basically based off icing. It's based off a lattice. So instead of like having the linear number of arbiters, you have kind of like a lattice space of they talk to each other. It's kind of like an atom kind of design. And since it's a chaotic model, it's actually performs much better against machine learning models. So far, I haven't seen any paper attacking that model, so it's still secure. But who knows? Maybe next year, somebody comes up with like an attack to icing path models. Okay. Any questions? Okay, let's do the final presentation.
Share the slide.
Okay. Are you able to hear?
Okay, stop here.
Sure.
It's this wave that it's all.
No, I didn't.
It just. It's accurate. It's because wave that it.
No, it was striking me before.
Oh, wasn't it?
Yeah. It's like I choose you.
Yes.
It follows you.
Yeah, I guess it is.
Chosen one.
All right, go ahead.
Okay, so good morning, everyone. Our presentation is about this paper called Flipping Bits in Memory Without Accessing Them. This is basically a study on DRAM and disturbance errors and how that leads to potential for something called a rowhammer attack. And the paper also produces one possible solution to the rowhammer attack. So first of all, we'll get into some background in the hardware of DRAM and how it works and how this lends itself to potential for disturbance down the attack vector. Basically, in order to store a bit in DRAM, we store it in a capacitor. In DRAM, we have a 2D array of cells, and each cell has a capacitor and an access transistor. This capacitor has either a charged or discharged state. Of course, charge is not just something that's binary, that's discharged or charged. So there's areas in between, and we basically have some cutoff charge. If it's above that charge, we call it charged, and if it's below, it's discharged. Now, this becomes problematic if we're somewhere in the middle, and it's a little bit more ambiguous. We have a little bit of a less robust system. For example, if we're very close to the middle and it's supposed to represent clearly charged, but we have some noise and it becomes slightly lower charge, we might be interpreting it as a different bit than it actually is. So here is a 2D array of the cells, and each of those circles represents the capacitor with our data bit value, and then an access transistor, which is connected to the capacitor. You'll notice that the access transistor connects the value in the capacitor to the word line and the bit line. And those correspond to the word line is connecting horizontally all the cells in a row, and then the bit line connects vertically down to the row buffer. The row buffer is actually sort of it's kind of like an API on where our process can actually read our DRAM data from. We can't read directly into the memory. We have to use, we raise the word line to a high voltage, and this basically connects the access transistor and pulls our values down from the capacitors into the row buffer where we can actually read them. And we basically can control this using the DRAM controller, which we'll talk about the instructions on the next slide. So in order to access DRAM, we have a few different steps. The first one is called open row. Like I mentioned, this raises the word line voltage, so you can actually pull the value down into the row buffer. And note that when we read something from the capacitors, we actually destroy the value that was there previously, and so we need to rewrite the value back in. And then when we read write column, we basically take our row buffer and we can pick out specific bits if we don't need the entire word, or if we need to change one of the bits, that's what we would do. And then close row is going to lower the word voltage on the word that we finished reading so we can read another one, and then it's going to clear the row buffer so we can transfer a new word of data from a different line. And then note that refresh basically has the same circuit as activate, where it reads something and then rewrites the value in, but the benefit to refresh is we don't actually care what the value is, so we can do multiple rows and refresh those bits in rapid succession instead of doing individual instructions for each one.
Okay, so one of the important things here that is to note is that the capacitors inside of all of these cells in DRAM slowly leak charge. So this is probably why a DRAM is volatile. When you turn on the computer, everything gets lost, right? So the thing to note here is that every time we open a row, we rewrite the value back to a clear charge or discharge state. Now, in DDR3, the specification guarantees that our values stay readable for 64 milliseconds. And what this means is that in order to ensure no data is lost, we need to refresh every row at least once every 64 milliseconds. And this is an operation that's done automatically by our memory controller. Now, this is where DRAM disturbance errors come in. When a word line's voltage is toggled repeatedly, our cells actually leak charge in the adjacent, the cells in the adjacent rows leak charge much faster than when they're just normally sitting around. So what would happen if we just kept on accessing two rows adjacent to a victim row in the center?
So this basically gets into the problem, which is the row hammer attack. We take this intuition of being able to cause a disturbance by rapidly changing the word line and reading from the same row. And we actually look at testing methodology to see if this is a practical attack and what we can do about it. So we have assembly code on the left here, which we call code 1A, and this was tested against basically a control. And what happens here is we pull two lines from memory using our move instructions, and then we flush the cache so that the processor isn't storing the thing. That way, when we do the jump back to the beginning and we basically loop this over and over again, instead of caching those lines in memory, we're basically able to access the same two rows every single iteration. And the question then becomes, what if we were to pick X and Y such that they were close to the same row in the middle, and we were to run this millions of times? And then we discover that we have sort of a big problem with the row hammer attack. Next slide.
How did you find this?
So this was tested against a control. In the control, we only read one row from memory, and we read different bits of that row repeatedly. And the processor can sort of optimize that a little bit in that instead of pulling it, opening and closing the row over and over again, we just leave the row open because there's no other memory accesses to the same place. And when we compare this to the control that I just mentioned, the control has no bit flips in any of the processors or systems listed here. But you can see that there's thousands of bit flips in the three Intel systems, Sandy Bridge, Ivy Bridge, and Haswell, from both 0 to 1 and 1 to 0. And then the last one is an AMD system called PowerDriver. The number is lower, but it's all compared to 0 with the control. So you can see that this code is like clearly has malicious potential. And this is what we dub the row hammer attack.
All right, so now we'll talk a little bit about how they evaluated the problem here. So one thing that they did was they took an FPGA like test bench and they tested 129 different DRAM modules, all from varying manufacturers, manufacturer dates and such. And what they found was 110 out of 129 of these were susceptible and lost a significant amount of data. So what they did is that they tested different
refresh and activation levels, intervals. Refresh intervals being like how long does it take until they actually refresh the memory, which in DDR3 specification, we said it was 64 milliseconds, but they decided to go ahead and try a bunch of different things, starting anywhere from 0 to 128 milliseconds. And as you can see from that graph there, the longer time that we spend before refreshing each of our cells, the larger number of errors accumulates. Additionally, the activation interval is how often they were telling the memory controller to open and close. So that was basically the time spent between closing a row and reopening another. What they saw, I don't have a graph here, but as they, of course, decreased the activation interval, they saw that the number of errors increased as well. The last graph here is basically just talking about the physical row address difference and the correlation of that to errors. What this graph is basically showing us is that the physical rows adjacent to the ones that we were accessing were actually the ones that lost the most amount of data. As you can see, the ones that were -1 and 1 lost a significant portion of the data, as well as some of the ones in the later, farther away in the row address. This might be attributed to the physical address and the physical area on the chip that they're actually located. The physical rows versus the address that they are might be kind of different, so they might be kind of intertwined with like 1, 7, and some other encoding. So that's why some of these chips were a little different. And then additionally, here's some findings that they found from while they were evaluating this problem. Of course, the most important thing was that row hammer is repeatable. Not only did this happen in when they saw victim cells lose data, if they did 10 iterations, then more than 70% of those victim cells would continuously, repeatedly, in every single iteration, continue to lose their data. Additionally, they found that weak cells being cells that where you don't refresh them for an extended period of time, they're more susceptible to losing data. That had nothing to do with which ones were victim cells. So this has something else like electrically, physically going on. Additionally, ECC memory, which is error correcting code memory, was unable to prevent all row hammer errors. It prevented it a little bit, but unfortunately, it's still a bit of a problem. Additionally, they found that errors are data pattern dependent, which means depending on what data is actually inside the memory, you might see different responses to this attack. And then additionally, only a small fraction of cells leak enough to cause an error. So it was a small portion, but still enough to be susceptible to attack.
Okay, so based on this problem that they characterized, the authors first considered some intuitive solutions, and then developed their own solution from there. Here are the approaches that they considered. Obviously, one of them is to just design better DRAM, but we're not really going to be talking about that design choice in here. The first one that they considered was that the manufacturer was to just take each DRAM module and test it. And then if there were particular cells that were susceptible to be victim cells, they would remap them or those addresses to different places so those aren't used. But the problem with this is an exhaustive search for one module could take days because of the amount of memory and then the access patterns that you would have to try to actually look and see for the row hammer attack. And this becomes really impractical when you consider the scale of manufacture. Then the second one, which builds off the first one, is what if when the user gets the DRAM module, they were to test it themselves. And they would basically be able to remap the address to somewhere else or just not use the address. But then the problem is the distribution of the victim cells or cells that are susceptible to the attack is not really predictable. So you can have a RAM module that has way too many of them, and then you don't have enough basically spare cells in memory or spare rows in memory to remap everything. So that's another problem with that. And it's kind of an unfair burden to put on the purchaser of DRAM. And the third one, basically the idea is that every time we refresh or read from a row, we are resetting the capacitor to a very clear high or low value, and basically reducing the ambiguity if it's been sitting there unrefreshed or with a lot of activations around it. And so the intuition is if every time we read something, we refresh the neighboring rows or we refresh all the rows, then we're going to be refreshing really frequently, and the probability of a bit flip becomes basically 0. And then the problem with this, obviously, is that the probability of bit flips over thousands of iterations is pretty small. So this becomes very unnecessary overhead. You're going to be refreshing rows way more often than you need to, which is a waste of energy and overhead because it ends up being slow. Your DRAM controller has to do all these refreshes and accesses. So then the intuition building off of that one is, what if we only basically had a counter or something like that to determine which rows are being hit more often, and then once we hit a certain threshold, we could refresh the adjacent ones to prevent a row hammer attack. And then of course, the issue with that is that you actually have to have like a counter for every single row in memory, and it becomes really, really expensive to do the math and store all that data. And the intuition builds up to the question, how can we prevent a particular row from being hit so often without refreshes in adjacent rows that we have bit flips, but also not be doing a lot of math to figure out when this is.
Okay, so here's the proposed solution. They called it PARA. And basically what this is, it's a low overhead and inexpensive method to solving this problem. So PARA stands for probabilistic adjacent row activation. Basically what this means is that instead of having to count how often each row is accessed, what they do is just using probability. So they every time that a row is accessed, there's a probability that's calculated that determines whether or not a row adjacent to it is going to be refreshed, and then another 50-50 coin flip to determine which adjacent row, either on the left side or the right side, which they're going to refresh. Basically, what this means is that as one row is refreshed more often and more often, the chances that the adjacent rows are also refreshed is going to increase as well. So the positives for this solution is that it's stateless. This means that it needs no memory and it does not need to store anything. So there's not a heavy memory cost overhead, as well as as I talked about, it's basically certain that if you refresh one cell a significant number of times, then it's certain that the adjacent rows are also going to be refreshed as well. So what they did is that they tested this solution theoretically and in simulation. In theory, they found that if it takes like 100,000 refreshes of one row to cause a bit error flip inside one of the adjacent rows, what they did is that they decided to set our probability to 0.001, which means that for every row access of one row, there's a 0.1% chance that one of the adjacent rows is going to be flipped. And then, refreshed. And then what they found is that within 1 year of running an adversarial attack, so 1 year of just hitting the same row over and over and over again, there was an extremely low chance of an error in one of the adjacent rows, which is basically negative. And then additionally, they tested the performance overhead in simulation. They did 29 commodity DDR3 benchmarks on a simulation, and they ran it with a little bit of a higher chances and explanation in the paper for why they used that. But they found that this was only an average of like a 0.2% degradation in performance, so not really a big deal. That maxed out at like 0.745. So the performance there is very, very possible.
Okay, and then here are some follow-up works that built off of this initial paper. The first of them just test this on an ARM platform instead of the x86 machines that were tested here. And they found that the ARM machines are also vulnerable to the same attack, and it's not just limited to x86. Then the second one here tests Rowhammer on newer modules like DDR4 and LPDDR4. And since these modules tend to have like even more densely packed cells in the RAM, this actually increases the chance of bit flips because everything's closer together. And there's more potential for disturbance. So these newer modules end up being even more vulnerable to Rowhammer than the DDR3 modules that were studied in this paper. And then the last one, basically this one starts with the idea of memory deduplication, which is that you can start from a physical address and then reverse engineer sort of the virtual address with some certain conditions being met. And they found that by combining that with the Rowhammer, you could do basically more complicated attacks where you could reliably flip certain bits. And this basically shows the potential for Rowhammer to be used in larger attacks rather than just like randomly flipping some arbitrary bits. And then here are our discussion points. So the first one is what hardware changes can we make to the DRAM modules? Since we noticed that DDR4 ends up being more susceptible to Rowhammer, what changes could we make in the future in the design of the DRAM such that this attack can be resolved at that level. And then the second one is what kind of solutions would there be to identify malicious software that have DDR row hammer attacks? And basically this would be like identifying access patterns and stuff like that. And this is kind of hard to do at like the system level because there's different processes that have different address spaces and it becomes really complicated. But we're wondering like, could there be a potential way that you could scan software for this liability? And then the third one is it possible to select specific bits to flip in DRAM? There's some difficulty with this, basically knowing like where variables or information maps to the physical space in DRAM. And then how could this be used in a more ambitious attack and what do we have to worry about? So those are our discussions.
All right, thank you so much. Yeah, Rowhammer is, we briefly discussed it in the class, but, oh, you turned it off? That's actually. So Rowhammer is one of those attacks that we didn't extensively talk about in the class, but it's also kind of like hardware related. The idea is that, just because of the way that we physically implement. Yeah, you have a question?
Yeah.
So go ahead.
How likely is multi-vector in a word? Because ECC is pretty like standard practice in this. It does solve this in
But Rowhammer people have shown that you can flip more than one basically, and you can use a much more heavier error correction, but that comes at an overhead. So I mean, there are solutions for Rowhammer. It's just it just increases the cost. But yeah, going back to what I was trying to say is generally the idea is just because of the way that we physically implement DRAMs, there is this potential for this type of attacks. And generally, these are kind of categorized as, we can call it fault attacks or hardware attacks. Rowhammer is one of them, where the idea is that the attacker tries to kind of like leverage the physical characteristics of the system in order to attack the system. There's another class of attacks called cold boot attacks. I'm not sure if any of you have heard about it, but generally the idea is that DRAM for sometimes, I mean, it's a volatile, but it's like it retains data for about like 2 to 3 minutes, 4 minutes, something like that. And what people have shown is that when you turn off your computer, you can take out the DRAM and connect it to your own computer and basically read off everything from your DRAM without any problem, right? And just that 2 to 3 minutes, if you're quick enough, you can actually collect all these things. So it's kind of like a cold boot, cold boot attack in that sense. And that's kind of like also kind of like leveraging this fact that there is physical characteristics of your memory that you can leverage. Generally, the point is that there is another class of attacks, is fault attacks, that you can mess up with the way that the implementation of the hardware is and use it for your own benefit as an adversary. And row buffer is one of the key ones. It's actually these days also again resurfacing in the research community, and people have started thinking about it more because it's serious. Yeah.
It does also happen inside the CPU itself, like the cache.
On the cache, the bit flips doesn't happen. So it only happens at the DRAM because just the way that the DRAM works, because you continuously access one row and the access of your row impacted your nearby memory cells. In cache usually use SRAM, which is like very different than DRAM, the way it's implemented, and accessing rows doesn't impact. Does that make sense?
You could still have voltage fluctuations in the cache.
You can do voltage fluctuation. So there were like, remember we had an attack where the attacker plays with the voltage, and that creates some bit flips on the data path of the processor. For cache specifically, it's difficult, but for the data path, you can flip it. But generally, row buffer is very different. Rowhammer is very different than the others because Rowhammer attacks DRAM. The memory you use usually on chip is SRAM.
What is it about this code exactly that makes it so hard on memory?
That's just an implementation issue. It seems that they're just So two things usually, there is a memory leakage, which means that you use some memory, but you never free it. And you kind of like hug all the memory. That's one big problem of Chrome that's it's known to have memory leakage. So essentially the actual usage of memory is pretty small for Google Chrome, but since over time it's never actually released that memory, it's just cumulative. So it's like, accumulate more and more memory. And that's one thing, it's just an implementation issue really. I think these days they kind of fix it most of the time. So recently I saw that they actually showed that Chrome on Mac is faster than Safari. I don't know if it's, these days I'm actually using it and pretty happy with it. But I mean, Chrome, and another problem it has is privacy problems, right? So that's not great for your privacy, unfortunately. But again, it's your choice. Convenience, right? It's like it has everything you want. But on the other hand, it's not private.
Depends on if you trust the war or not.
What's that?
Depends on if you trust the war or not.
Yeah, exactly. So it's not famous for its privacy, unfortunately, right? So for example, Safari these days is banking on the fact that, oh, we are private, we don't sell your information. Versus Google Chrome is not, it's not that. Okay, guys, any final questions? Thanks for sharing my cat's pictures and myself. That's fun. All right, so I'll see you guys on Thursday. And then if we don't, good luck. It was great having you all in the class.
Thank you.
Yeah.